Hi everyone and welcome to this ARCHER2 webinar. Today we have Peter Boom from the University of Manchester giving us a talk on a recent ARCHER2 ECSE project. There will be time for questions at the end of the talk, but if you want to ask anything during, then please feel free to write them in the chat or raise your hand. So without any further ado, I'll hand over so that we can get started.
Thank you very much for that introduction. Hi, everyone. Thank you for coming today. My name is Peter Boom, and I'm a PDRA at the University of Manchester. I believe also here today are my colleagues, Professor Andrei Zhivkov and Professor Lee Margetts. This project was looking at integrating discrete exterior calculus into the ParaFEM finite element library. This was a follow-on to an EPSRC fellowship held by Professor Zhivkov that was looking at developing discrete exterior calculus for applications in solid mechanics. This is kind of a report on the activities that we've been doing as part of the ECSE 01-12 project. So I realize this is an HPC talk, but I'll start with just one or three slides on the scientific aim and some of the mathematical underpinning that will help us discuss some of the computational aspects of the project. So the overall scientific aim is to model processes evolving on the discrete mesoscale structures of materials. And we're interested in processes that are both heterogeneous and discontinuous. So one example might be fracture, processes that are inherently multidimensional. So for example, if you think about diffusion through a material, you might get different diffusion rates through the grains of a material as opposed to along its grain boundaries, and processes that are inherently multiphysical. To tackle this challenge, in this project, we're interested in discrete exterior calculus, even though more generally we're interested in discrete forms of exterior calculus. This is just one particular discrete form of exterior calculus. There's others that we're also interested in. The idea here is that rather than looking at continuous fields and how we can approximate them discretely using finite elements or finite differences, things like that, we want to develop models that are discrete at the fundamental level, that represent the physics on discrete entities through their geometry and their topology. So you can think of a few different things that you can compute using this approach. So if you have a value that exists at a node, you can take the difference between two nodes along an edge and get something similar to a gradient. It's actually just a difference, a directional difference, not a gradient. The gradient would be evaluated or be intrinsic to the length of the edge. Likewise, if you had a value that lived on an edge, perhaps representing a vector field of some sort, you could evaluate something similar to a curl on faces by combining different edges. And again, it's somehow intrinsically linked to the size, the geometry of that face. So you can see that these different operations increase your geometric dimension each time. And so to be able to relate higher dimension objects to lower dimension objects, we also construct a dual. So if you look on the left, we have in 2D a primal mesh defined by triangles and its dual defined by, in this case, it's a Voronoi dual that's shown in red. So through the use of a symplectic mesh and its Voronoi dual, we can mimic a lot of operations that we might be familiar with in vector calculus. However, they're intrinsically linked to the geometry of the mesh, and we define the physics on these geometric elements. One of the things that's important to notice here that will come back later in the presentation is if you look at the dual cell here in the top corner, which is a hexagon, it overlaps with 6 primal triangles. So when we think about partitioning our mesh and parallelizing it, we may have elements that are distributed. And overcoming that is one of the challenges that we had to think about in this project. So as we've already mentioned, this presentation kind of summarizes the activities of an ARCHER2 CSE project, where, again, the aim is to integrate discrete exterior calculus into a finite element library called ParaFEM. And I'll come back to this slide in one moment, but I'll introduce to you the two libraries that we're working with. The first one is called ParaGEMS, standing for Parallel Geometric Mechanics of Solids, which is an open source module library that was developed through a fellowship at the University of Manchester, an EPSRC fellowship. It's a Fortran 90 library parallelized with MPI, and it implements discrete exterior calculus. It's compatible with triangle and TETGen meshes, and is really designed to be a library on which you develop mini apps for solving different problems. At the start of the project, most of the problems we were solving were diffusion dominated problems. And the code uses PETC for solving the resulting system of equations. The code is available on Bitbucket if you are interested in it. Just a little bit more information that's not on the slide. At the start of this project, we were able to show 80–90% parallel efficiency on up to about 1,000 processors. But we really want to leverage tools that are already highly optimized for larger scale problems. So rather than solving meshes that have millions of cells, we want to scale that up, upwards of 1 billion cells, for example. And to do that, we want to show that we can scale well beyond 1,000 cores to tens of thousands or hundreds of thousands of cores. And so we're really interested in leveraging the capabilities of the ParaFEM finite element library to do this, to both accelerate our development of DEC, but also be able to take advantage of the multiple physics that are described in the ParaFEM library to do coupled simulations. So this is also a code written in Fortran 90 with MPI. It's an open source library that's available both on the ParaFEM website and through GitHub. And in the past, it's been shown to scale on tens of thousands of cores for problems with over 1 billion degrees of freedom. So it really kind of fits what we're looking for in terms of where we want to end up with being able to solve DEC-based problems. There's also a textbook that's associated with this that you can find on Amazon. So we want to use discrete exterior calculus. We have a research code that's developed that's shown good scaling on up to 1,000 cores, but we want to really integrate this with the finite element library ParaFEM to be able to extend this to much larger problems. Target for this project was 80–90% parallel efficiency on tens of thousands of cores and 70–80% parallel efficiency on 100,000 cores. We were also want this to be a long-term software project, and so we invested time in software sustainability and working with the user and developer community on Archer. So initially, when we were thinking about this project, we had the ParaFEM library and the ParaGEMS library, and the idea was that we wanted to solve coupled problems where the bulk of the processing would happen in ParaFEM, and then the discrete analysis that we wanted to do would be handled by the ParaGEMS library. So ParaFEM would solve the basic problem and provide boundary conditions for specific areas of interest where we wanted to apply our discrete analysis, and that would in turn give element properties back to ParaFEM. And this was kind of the framework that we had in mind when we started the project. And so we did invest a fair amount of time into improving the performance of the ParaGEMS library so that we could integrate it in this fashion. And I'll talk about in a little bit how that shifted throughout the project. So the first step was obviously to get the software running on Archer, and the software is developed with make files and configuration scripts. So we develop or include files for different systems, and we did this for the different compilers available on Archer. When we were developing the software locally, we would compile our own version of PETSI, and that's where we started in this project on Archer, was just to compile our own version of PETSI, but PETSI is a module that is available. And so we looked into using the module available on Archer and the configuration and optimizations that have gone into building that software. Unfortunately, it was missing one of the packages that we were making use of. But fortunately, they provide all the configuration files in a GitHub. So we were able to modify those scripts and get the necessary packages. And we did do some performance comparison between our own compiled version of PETSI and the one that was configured through this repository. And we didn't notice much difference, but if performance optimizations do come down the line, then we can make use of them through pulling updates from this repository. We did put a fair amount of work into profiling and optimizing the ParaGEMS library on its own. When you are writing new software for the first time, you're trying to test the limits of it and often do a lot more computation that is necessary. So we started identifying bottlenecks in the software and eliminating, I've put this in quote, dead weight, but basically things that we used to test the limits of our software. And basically the goal was to make it more specific for the applications we were interested in. So we had less information at the end of our simulation, but the information that we were removing was information that was rarely used. We also noticed early on that I/O was a fairly significant bottleneck. And so we looked at the ParaFEM routines to get inspiration on how to better process our input data. We also were able to combine information into fewer input files. So rather than having a file that listed all the faces that were in our mesh and a separate one that listed all the boundary conditions on those faces, we could combine that information to minimize the I/O that we were doing, basically make it a denser operation. So this yielded a fairly significant reduction in CPU time. So for a 6 million cell mesh on 128 processes, we were getting a 2/3 reduction in CPU time. Again, this is a very large reduction. A lot of that came from minimizing the amount of extra information that we were computing that wasn't strictly necessary for solving the problem. And then through a portion of it was through our I/O improvements. We also worked on extending the range of application of the library and the things that we could do with our mini apps. So initially we were only able to solve problems on tetrahedrons, but ultimately the microstructures that we're interested in mimicking more closely resemble Voronoi cells, which are the dual to the tetrahedrons. And so we were able to look at the dual formulation and comparisons between a 1-field and 2-field formulation, looking at simulations in 2D and 3D, looking at different types of physics, and then also looking at time-dependent problems through implicit multi-step Runge-Kutta methods, as shown here on the right. Again, with a view for this to be a long-term software project that it can be used in research and engineering applications through industry partnership. We also looked at code sustainability. So before we ever started writing the software, we put a lot of time and effort into planning the data structures and the information flow and how things fit together. We also spent a lot of time and effort as we were writing the software to make sure that it was well commented and that all the functions and subroutines had appropriate headers. So when we started looking at automatic documentation, most of the work that went into that was just setting the appropriate comment characters and setting the keywords. So we are able to do automatic documentation both with RoboDocs and with Ford. The former giving more user-defined or developer-defined information, and Ford extracting more information from the code itself. So both are available with the software. We've also looked at improving the new user experience through improving the README installation instructions, creating examples and tutorials for some of the mini apps that we've developed. We're also developed a number of testing routines and programs to ensure that the code works correctly as we continue to develop. So as I mentioned, this was our initial plan with integrating the software. So once we had improved the performance of ParaGEMS, we were looking to start integrating. But we realized that a lot of the information that we want to input into our solver is going to be common. A lot of the parallel partitioning, initialization that we want to do is going to be common between the two codes. The solver is going to be common between the two codes, and obviously we're going to want to output in similar formats. So we decided that we wanted to take a slightly different approach and basically kind of develop a mini app that called only the necessary functions and subroutines specifically for DEC, and that we could do the coupling between finite elements and discrete exterior calculus if we needed to within the mini app rather than having two running side by side. And so we decided to take some of the mini apps that already existed for the ParaFEM library and use those as kind of a template. I don't know if this is too graphic, but rip the finite element heart out of the mini app and transplant in a new DEC heart, if you will. So first step that we did was move the code from Bitbucket to GitHub. The code is still available on Bitbucket, but we've also added it under the GitHub umbrella of ParaFEM. It will be available there if you're interested to download it. Discrete exterior calculus works with simplices. So in 3 dimensions, that's tetrahedrons as the fundamental cell, or the Voronoi dual. Whereas the mini apps that we were interested in working with in ParaFEM used a variety of different elements, specifically hexahedral elements. And so we wanted to look at decomposing the hexahedrons into tetrahedrons so that we could apply our discrete exterior calculus. I've read that there is actually 174 possible decompositions of a hexahedron to tetrahedrons. But the approach that we followed, once you've split quadrilateral faces into triangles, then you end up with 64 possible ways of decomposing our tetrahedron, or sorry, our hexahedron. And I was looking at ways to select the decomposition that minimize the amount of negative areas and volumes in the dual Voronoi mesh. From both a mathematical and a technical standpoint, having negative areas and volumes is not an issue. It's one of those things that falls out in the math, if you will. However, it's always nicer to see positive values than negative values. So I spent a week trying to develop a clever algorithm to decompose the hexahedron into tetrahedron. And at the end, with nested loops and conditional statements, I found it just more efficient to have a select statement. So the process is as follows. We divide the quadrilateral faces into triangles. And then once you've divided the 6 faces into triangles, then you can generate a number, a binary number that allows you to populate your select case with your 64 different possibilities. So now that we have tetrahedrons that we can work with in our code, we want to start implementing discrete exterior calculus, specifically using the functions and subroutines that we developed in ParaGEMS. But ParaGEMS was developed with awareness of ParaFEM, but also separately. And so it has a different structure and parallelization mentality than ParaFEM. So coming back to this idea that your primal and your dual mesh overlap, and specifically that a dual cell will overlap multiple primal cells, and one primal cell will overlap multiple dual cells, and so on. The mentality that I used when I was developing the software was to process the complexes in large chunks. So assume that you have on each process essentially a subcomplex. A subcomplex, and process it together. It's a little bit difficult for me to explain, but the complexes are kind of processed as a whole rather than cell by cell by cell. And this meant that there is some overlap when you split a complex between processes and multiple processes, and that's one of the things that you have to take into account when you are organizing your cells to minimize communication overhead and redundant information. Whereas the approach with ParaFEM, I mean, there's still going to be communication overhead, there's still going to be some repeated information, but fundamentally, the data is computed, your physics is implemented element by element, and using superposition is then added up rather than computing everything as a whole. So we had to think about how we were going to integrate these two ideas together. And the solution is kind of obvious when you get there, but it took us a little while to get there. And the way that we overcame this is recognizing that a single cell and its dual is a valid complex, and you can compute a number of single complexes and add them together, and you will recover the same integrated complex that you wanted to start with. And so this is kind of the approach that we use. This is with triangle elements or mimicking triangle elements, but you can also do this with quadrilaterals. I'm giving a lot of examples in 2D because it works out graphically better for the presentation, but this naturally extends to 3 dimensions as well. So here is an element that is composed of 2 simplices, 2 triangles, or decomposed into 2 triangles, and its Voronoi dual. And we can then add those up in a similar way using superposition and to recover a much larger complex. And we can do this both locally and globally across multiple processes. And in this way, we can use many of the ideas or the mentality of finite elements and still use our discrete exterior calculus. So this is one of the mini apps that we took from ParaFEM and redeveloped using discrete exterior calculus. So this is just one subsection of the code where your system or the system matrix is built. And so the first thing that we wanted to do to integrate the discrete exterior calculus was we wanted to convert if any exists, are hexahedrons into tetrahedrons or quadrilaterals into triangles. We then needed to calculate the associated topology and geometry needed for discrete exterior calculus. And then we wanted to replace this last section here where we would traditionally in finite elements look at the Gauss points and do the integration and replace it with our discrete exterior calculus formulation of our problem. And this is actually a very small portion of the mini application, and the rest stays the same. So the initialization and I/O remains the same, and boundary conditions can be implemented for this particular problem in a very similar fashion to finite elements. And then once we have our system matrix, then we can use the same solver and the same output routines to output the solution. And so this is actually a fairly small modification to the problem, or sorry, to the program that allows us to implement our discrete exterior calculus. This also shows that if you wanted to do coupled physics simulations or coupled discrete exterior calculus and finite elements, it would be fairly straightforward to do it through this form. So once we had our mini application, we could do some parallel scaling studies. So this shows, the colored curve shows strong scaling, and the dashed curve would be our weak scaling. And we can see that at least on our largest meshes that we have both excellent weak and strong scaling. And then as the number of elements per core that we have decreases for smaller meshes, then we see that there are aspects of the code that don't scale well. So that would be, I guess, our serial overhead and other communication overhead. So here are just two aspects of the code. Rather than showing, I'll talk about the scaling of the overall code in a minute, but this just shows that the portion where we're introducing the discrete exterior calculus, the construction of the system matrix, scales really well. And we're still making use of the same solver that ParaFEM uses, and as has been demonstrated in the past, it also scales well. So one of the things that was an issue with the ParaGEMS library by itself and ends up being the bottleneck in the joint ParaFEM plus GEMS code is I/O. And there's a few things to say about I/O. So the I/O routines that we've been using in this project are reading ASCII files, and that is predominantly because of our pre-processing workflows. Our ultimate goal is to get to binary files, which experience has shown us that can yield several orders of magnitude reduction in the overall CPU time using binary I/O rather than ASCII I/O. Excuse me. And the way that these I/O routines are set up is that the root process reads it and then distributes it to the adjacent processes, which in many cases is sufficient. So it turns out that in the simulations of steady diffusion, which is a very simple problem to solve, I/O ended up being a fairly large portion of the overall solution time, meaning that if you look at the overall scaling of the software, it doesn't look very good. However, if you're running tens of thousands of time marching steps, or if you're looking at the propagation of cracks over 1,000 iterations, while that won't eliminate the scaling drawbacks of this type of I/O, it will diminish them. And especially once we move to a binary I/O, then it will become even less of an issue, but it's something to keep in mind for the future. Parallel I/O using MPI is something that we have considered. It is something that I've worked with in the past in other codes and made good use of. The reason why I didn't implement it with the ParaGems library is because while it may be clear what portions of the file, for example, a node file, go to what process, it's less clear what portions of an edge or a face file go to which process, at least the way that the files are set up currently. So either some pre-processing would need to happen beforehand to make use of MPIO, or some more work needs to be done to make use of that in the future. Yeah, this just saying that we have binary I/O routines already existing for ParaFEM. So once our pre-processing workflows improve, then we can make use of that. So in summary, between the improvements that we made to the ParaGems library and through integration of discrete exterior calculus in ParaFEM, we were able to recover approximately 100 times speed up for a 6 million cell mesh with 128 processes. So a lot of that speed up came from, again, limiting what we're actually computing and minimizing unnecessary computations just to get information about the problem that is not going directly towards the solution. So it may be that if you're solving a different type of physics or a different problem, or you need to know information about the entirety of your complex, that you can put that information back in. But a large portion of that speed up just came from removing that unnecessary computation and also improving our I/O routines. I don't know if I mentioned this earlier. What I had wanted to mention about improving the I/O routines, initially our root process was doing a lot of processing before sending it to the adjacent processes to minimize communication, whereas we kind of changed our paradigm and basically sent more information to the adjacent processes, but let them take care of some of the processing. And that way, there was less demand on the root process. We were able to accelerate the overall routines and distribute the workload more efficiently. As we saw, we were able to recover excellent both weak and strong scaling of our core routines on just over 16,000 cores. And this is mesh dependent. So the largest mesh that we were looking at had about 200 million cells in it, and with an eye to looking at larger meshes with over 1 billion cells. We're hopeful that we can scale on a larger number of cores, but future work will definitely include seeing if that's true and how we can optimize the code for those larger meshes and larger number of processing cores. I/O in some sense going and known performance bottleneck, ongoing performance bottleneck, at least for simple steady problems that we were considering in this presentation. But we both have an idea of how to improve that and the tools to do that. And like I said, depending on the problems that we're looking at, we can, it's not removed, but it can be diminished, and there may be larger things for us to focus on in terms of profiling and optimization. As a result of this project, I think we've demonstrated that we have an efficient tool to underpin new research using both discrete exterior calculus, but also other discrete forms of exterior calculus. A lot of the topological functions and geometric functions that we've implemented can be applied to other discrete forms of exterior calculus that is also under investigation at the University of Manchester. And we've also extended the possible use of the ParaFEM library, not only by introducing new mathematics, but being able to leverage the different types of physics that can be solved using ParaFEM, and couple that in close coupling with the discrete exterior calculus for material performance down the line, and study engineering applications. So future work, as I mentioned already, looking at how the code performs on much larger meshes, upwards of 1 billion cells, and how that will affect scaling beyond, the 16 to 32,000 cores that we considered in this project. One of the things that I've been thinking about over the Christmas holidays is trying to calculate critical core loading. So if we want a desired parallel efficiency, can we develop a number, something like a number of elements per core that will give us that efficiency? And is that a useful metric for a user who says, I have a geometry with a certain number of elements, or for us as developers, as we try to improve the performance of the code, can we improve that ratio as a metric of parallel efficiency? Integrating binary I/O and looking at implementing different NP-IO routines to minimize the I/O bottleneck. One of the things that I've been working on recently since Christmas is, because we're looking at these individual small complexes that are added together, the way it integrates with the ParaGems library means that we're not wasting memory, but we're doing a lot of reallocation, and so I think that can be improved. Also looking at how we can integrate broader forms of discrete exterior calculus. As we get more people using the code, they often are good for finding bugs, but also things that are not straightforward. So we're looking at developing better configuration scripts, and maybe even offering containerized versions of the software. And also looking at, while we have some testing routines and programs built into the code, they're mostly hand-coded. And so looking at using a proper testing framework like Fruit, for example, is something that we're interested to continue promoting the sustainability of the software. Thank you for your time, and I'm happy to answer any questions.
Thank you very much. That was great. Yep, so if anyone has any questions, then please, you can write them in the chat, or you can raise your hand and ask them using your mic. It's up to you. So there's a question in the chat. It says, very nice presentation. Do you have any link to a paper about the maths side and its application to solid mechanics?
Yes, that is a great question. The answer is yes. So I put into a chat a paper that we recently had published on linear elasticity based on discrete exterior calculus.
Thank you very much, everyone, for coming, and thank you again, Peter, for presenting your talk.
Thank you very much. Thank you, everyone, for coming. Have a good day.